The image on the slide shows the aftermath of a building collapse, vividly illustrating the impact of an earthquake. This is a powerful visual that underscores the title of this section. A violent pulse. Earthquakes are sudden and sometimes catastrophic events causing the Earth's surface to shake. This occurs due to movements within the Earth's crust or volcanic activity. As we can see, the damage can be extensive, affecting buildings and infrastructure, and posing significant risks to human life and the environment. Understanding the science behind these events is crucial for predicting and mitigating their effects. In this slide, we're examining what happens during an earthquake. Let's start with the first image on the left. Before deformation, you can see that the rock layers are not bent, representing the initial state of the rocks beneath the Earth's surface. Moving to the second image. As deformation occurs, the rock layers begin to bend elastically, similar to bending a stick in your hands. Notice in the drawing how the amount of bending is exaggerated to make it clear. This elasticity means the rocks are storing energy as they deform. Finally, let's look at the last image. Eventually, the stress becomes too great, and the rock breaks. This results in sudden sliding along a fault line, creating vibrations that travel through the earth, similar to the shock waves you feel when a stick snaps in your hands. These vibrations are what we experience as an earthquake. In 2011, the Tohoku earthquake struck Japan, causing significant destruction. On the left of the slide, there's an image showing the aftermath where some buildings collapsed due to intense ground shaking, illustrating the direct impact of seismic activity on infrastructure. To the right, there is a photograph depicting the tsunami that resulted from this earthquake. The image shows how the tsunami waves filled harbors and spilled over seawalls, demonstrating the secondary effects of such a powerful earthquake. This combination of shaking and tsunami caused extensive damage and loss. In this slide, we see the development of a new fault over time. Starting on the left, imagine a block of rock secured by two clamps. As one clamp is moved upward, the rock begins to bend, and small cracks, represented in the diagram, start to form along this bend. This stage is known as elastic bending. Moving to the center of the slide, these cracks eventually connect, resulting in a rupture that cuts entirely through the rock, shown as rupture formation. On the right, we see the final stage, slip and vibration. At this point, the rupture causes the rock to break into two separate pieces that slide past each other. The release of energy from this action generates vibrations, known as seismic waves, as indicated by the waves around the rock in the image. This sequence effectively illustrates how a new fault develops, from initial stress to energy release. Let's take a closer look at how we define the location of an earthquake on this slide. We have two key terms to understand: the focus, also known as the hypocenter, and the epicenter. The focus is the initial point within the Earth where the generation of seismic waves begins. This is depicted on the slide as focus A and focus B, marking where slips on the fault cause seismic activity. The epicenter, on the other hand, is the point on the Earth's surface that is directly above the focus, represented by epicenter A and epicenter B on the surface above each respective focus. It's crucial to differentiate between these two terms. The focus is located beneath the Earth's surface, while the epicenter is directly above it on the surface. Understanding this distinction helps in assessing the impact and reach of an earthquake. This slide focuses on seismic waves. We categorize these waves primarily into two types: body waves and surface waves. Let's start with body waves. Within body waves, we have P waves, which are compressional, moving by pushing and pulling, similar to sound waves through air. allowing them to travel through both solid and liquid layers of the Earth's waves. On the other hand, are shear waves moving perpendicular to the direction of propagation and can only travel through solids, which makes them slower than P waves. Now, moving on to surface waves, confined to the Earth's surface. The first type is R waves, known for their vertical undulations, creating a rolling effect. L waves, the other type, are responsible for the horizontal back and forth movement. Due to their motion, surface waves typically cause more damage during an earthquake because they affect structures on the surface more intensely. Let's take a closer look at body waves, which can be broken down into compressional waves and shear waves. Compressional waves, or P waves, are generated by pushing and pulling on the end of a spring. As shown in the upper part of the slide, notice how the diagram illustrates the vibrations moving parallel to the direction of wave movement. A key feature of compressional waves, moving to shear waves, or S waves. The lower part of the slide depicts these waves produced by moving the end of a rope up and down, with vibration direction perpendicular to wave movement, distinguishing shear waves from compressional ones. These visual examples help us differentiate between the two types of body waves as they pass through materials like rock. In this slide, we see a depiction of two types of surface waves, L waves and R waves. On the left, the L wave illustration shows how the ground surface undulates back and forth, resembling a slithering snake's motion. Important to note as these waves move horizontally. To the right, we have R waves, where the visual demonstrates how these waves cause the ground to move up and down. Notice the circular path particles follow underground as R waves pass, combining both vertical and horizontal movement, distinct for making the ground surface rise and fall. Understanding these differences is crucial for interpreting seismic data and how different surface waves affect the Earth's crust. The slide illustrates the functioning of seismometers, essential tools for detecting and measuring ground motion caused by earthquakes. On the left, we see a vertical motion seismometer capturing up and down ground movements. Next to it, a horizontal motion seismometer records back and forth motion. Below, there's a diagram showing how these devices function over time. Before an earthquake, the seismometer's pen traces a straight line on a revolving paper-covered cylinder, indicating no motion. During an earthquake, the cylinder moves up and down, while the pen remains stationary, resulting in a jagged line capturing seismic waves. Understanding this mechanism is crucial for interpreting seismic data and assessing earthquake intensity and duration. This slide shows a seismogram, recording signals generated by various seismic waves. A timeline stretches from left to right across the graph's top. Different types of seismic waves are indicated at different timeline points. On the left, the P wave arrival, usually the first to register as they travel fastest. Next is the S wave arrival, followed by surface waves, which typically have the largest amplitude, reflecting the most energy and causing the most damage during an earthquake. Lastly, you see the aftershock, representing smaller tremors following the main event. Notice the roll of paper and cylinder on the right, illustrating how the seismograph records these waves continuously over time. To locate an earthquake's epicenter, we use different arrival times of P waves and S waves, displayed on a graph called travel time curves. Red lines on the graph represent these curves. The SP time, the time difference between S wave and P wave arrival at a station, is depicted by vertical distances between S wave and P wave travel time curves. To the right, we have a map indicating how circles are used to pinpoint the epicenter. If it's 2,000 kilometers from station 1, Draw a circle with a radius of 2,000 kilometers around that station. This circle represents possible epicenter locations. Repeat for 2 additional stations. The point where the 3 circles intersect is the earthquake's epicenter. Now, let's examine the modified Mercalli scale, which measures earthquake intensity by considering effects and damage, rather than energy released. Looking at Table 8.1, it ranges from I to 12. At Level 1, seismic instruments detect the earthquake with no noticeable damage. By Level 3, people indoors might feel slight shaking, resembling a passing truck. At Level 5, shaking becomes strong enough to wake most, with trembling felt and unstable objects potentially tipping over. At Level 7, noticeable structural damage occurs, with plaster cracks and chimneys possibly breaking. By Level 9, heavy damage is evident, with buildings shifting off foundations. At Level 12, total devastation occurs, with nearly all structures destroyed. The scale helps differentiate perceptions and damage levels, providing valuable information about earthquake impact on communities. To calculate the Richter magnitude from a seismogram, first, measure the amplitude of the largest wave, shown in the upper image as 23 mm. Then, calculate the difference in arrival times between S and P waves, known as S-P time, to determine the distance to the epicenter. Moving to the lower image, proceed by drawing a line from the point on column A, representing S-P time or distance to the epicenter. Extend this line to the point on column C, indicating wave amplitude. The intersection on column B gives the Richter magnitude. In this example, the line crosses at magnitude 5. In this slide, we examine the energy released by earthquakes and how it compares to other energy events. The graph on the left illustrates the exponential increase in energy release as earthquake magnitude grows, showing great earthquakes close to magnitude 9 or higher, releasing far more energy than the largest nuclear bombs. For example, the Chile earthquake in 1960 and the Alaska earthquake in 1964 are marked at the energy scale top, showing immense power. Visualize this with the Quake Lake earthquake in 1959, represented by a star on the graph, offering a reference point for understanding energy release scale. Additionally, note the Tonga eruption here, releasing energy between 4 to 18 megatons of TNT. Further contextualizing natural events' energy potential compared to man-made ones. Understanding these comparisons highlights the significant impact of earthquakes in terms of energy release. Seismic belts are highlighted on this map, showing the distribution of earthquake epicenters over several decades. Notice how these epicenters align along plate boundaries. The map uses different colors to represent the depth of each earthquake focus. Shallow earthquakes, occurring less than 50 kilometers deep, are shown in one color. Intermediate earthquakes, ranging from 50 to 300 kilometers deep, and deep earthquakes, from 300 to 660 kilometers, each have their own respective colors. This visual clearly illustrates the correlation between seismic activity and tectonic plate boundaries, emphasizing the concentrated zones where most earthquakes happen. In this slide, we examine divergent boundary seismicity, the distribution of earthquakes at divergent boundaries. At these zones, normal faults form along the ridge axis as the crust extends. In the first image, the movement of the hanging wall block downwards indicates a normal fault, characterized by crust extension. Additionally, strike-slip faults occur along active transform faults. These are illustrated in the second image, where one block slides laterally past another, with no vertical displacement. It's important to note earthquakes typically do not occur along inactive fracture zones. This information underscores specific conditions under which seismic activities manifest, helping us understand the mechanisms underlying divergent boundaries. In this slide, we examine transform boundary seismicity on continents. Focusing on the San Andreas Fault System in California, the map shows this system, including many faults spread over a 100-kilometer wide band, highlighting faults ruptured in major earthquakes of 1906 and 1857. The diagrams on the right show different types of faults. The top diagram illustrates reverse faults, occurring during crust shortening, where the hanging wall moves upward, and the fault is steep, typically around 60 degrees. Below that, thrust faults are depicted, also forming during crustal shortening. The main difference is the slope of the fault is gentler, less than 30 degrees, allowing for different seismic dynamics. Understanding these structures is crucial for anticipating earthquake patterns and their potential impacts. In this slide, we're looking at convergent boundary seismicity. In the upper left illustration, shallow earthquakes, represented by red dots, occur along the contact between the downgoing plate and the overriding plate, and within the plates themselves. Intermediate focus earthquakes, shown as yellow dots, and deep focus earthquakes, as blue dots, are located in the Wadati-Benioff zone, with most occurring between 400 and 500 kilometers deep. The illustrations on the right show fault formations due to crustal shortening. The top right image shows reverse faults, where the hanging wall moves up due to a steep fault angle, noted here as 60 degrees. Below that, thrust faults are depicted, with a gentler slope of less than 30 degrees. Understanding these fault types helps explain seismic activity mechanics at convergent boundaries. As we look at the slide titled Earthquakes Within Continents, we see a cross-sectional diagram illustrating various geologic settings where earthquakes occur in the continental lithosphere. On the left, we have continental transform faults like the San Andreas Fault, marked by lateral motion between tectonic plates, moving toward the center. The next section highlights active rifts, like the East African Rift, where tectonic plates diverge, creating tension areas leading to earthquakes. In the middle, we observe intraplate settings, like locations in New Madrid, Missouri, where earthquakes happen within a tectonic plate, away from boundaries, due to stress accumulation. On the right, we encounter collisional mountain belts, like the Himalayas, where the collision and compression of continental plates cause earthquakes. In the lower diagram, the boundary between brittle and ductile regions is depicted, as earthquakes tend to occur in the brittle section of the continental crust. Identifying different seismic activity environments within continents, excluding subduction zones. In 1959, the Hebgen Lake earthquake struck with a magnitude of 7.2 on the moment magnitude scale, causing a massive landslide that blocked the Madison River, resulting in Quake Lake. Tragically, 28 people lost their lives, marking it as the most severe earthquake in the Rocky Mountains. This earthquake was associated with normal faulting along the west side of the Madison Range. You can refer to the provided link for additional details about this historical event. The map on the right shows the affected region, indicating the geographical impact area around Hebgen Lake. Alright, let's look at the different ways earthquakes can cause damage, as listed on the slide. First, we have ground shaking and displacement, the most immediate earthquake effect, involving ground vibration, leading to buildings and structures collapsing. Next, landslides can be triggered by the shaking, causing significant damage to infrastructure and posing life threats. Sediment liquefaction is another consequence. Intense shaking can temporarily cause water-saturated soils to lose strength, behaving like a liquid. leading to sinking or tilting structures. Fire is also a major risk. Shaking can rupture gas lines and electrical wires, causing rapidly spreading fires. Earthquakes can also generate tsunamis, large ocean waves triggered by underwater seismic activity, causing coastal destruction. Lastly, disease can become an issue. Destruction of infrastructure leads to poor sanitation and conditions, potentially spreading illness. Understanding these mechanisms is crucial in assessing and mitigating earthquake risks. Let's look at quick question 7 on the slide, asking how tsunamis are formed by faulting at plate boundaries and which types of boundaries are associated with water upward displacement. We have 3 options: A, B, and C. Option A is convergent boundaries, where tectonic plates collide, typically with one forced beneath another, a process known as subduction. This action can definitely displace large volumes of water, leading to tsunamis. Option B is transform boundaries, where plates slide past each other horizontally, typically not displacing water vertically, less likely generating tsunamis. Option C is divergent boundaries, where plates move apart, while causing volcanic activity. They are also less likely creating tsunamis. The correct answer is A, convergent boundaries. In this slide, we examine how geologic records can help predict long-term seismic activity. The diagram shows a cross-section of subsurface sediment layers near an active fault. Various layers represent different geological periods. Past earthquake evidence is marked by features like sand volcanoes and disrupted beds, indicated by numbers on the diagram. These disruptions are key indicators, revealing when seismic events occurred. By analyzing these patterns, scientists can determine recurrence intervals, guiding predictions of future earthquakes.